Welcome everyone to part 3 in our series on grounded language understanding. Recall that in part 2, we focused on speakers. Speakers in our sense take non-linguistic representations as inputs and generate language on that basis. Listeners are kind of the converse of that. They accept linguistic inputs and try to make a guess about the state of the world on the basis of that linguistic input. For this unit, in terms of modeling, our focus is going to be on speakers. But I think it's helpful to have the listener perspective in mind as you create speakers. And you might even bring in the listener perspective as part of your original system. And I'll cover some techniques for doing that in the context of the rational speech X model a bit later in this series. Now, to make the speaker task meaningful, we need to complicate our previous task a little bit. So in part 2, we had for the speaker just a single color as input, and their task was to produce a description on that basis. For listeners, we're going to move to a more complicated task, and this is the task that's our focus for the entire unit. It comes from the Stanford Colors and Context corpus. And for that corpus, the context is not just a single color representation, but now 3 colors. And the idea is that the speaker is privately told which of those 3 is their target, and they produce a description that will hopefully communicate to a listener who's looking at those same 3 colors, which one was the speaker's target. And you can see that that gets really interesting and grounded very quickly. So in this first case, the 3 colors are very different. And the speaker simply said blue, and that seems to get the job done. And I think a listener receiving blue as input would know which of these 3 colors was the speaker's private target. When we move to the second context, though, we have 2 competing blues. They're very similar. And as a result, the speaker said the darker blue one. And the idea is that this comparative here, darker blue, is making implicit reference not only to the target, but to at least one of the 2 distractors. Third example is similar, teal, not the 2 that are more green. That's really grounded in the full context here. The speaker is not only identifying properties of the target, but also properties of the distractor in order to draw out contrasts. And I think the final 2 examples here are interesting in different ways. So here we have the target on the left. In the first example, the speaker said purple, and in the second example, the speaker said blue, even though these are identical colors here for the targets. The reason we saw variation is because the distractors are so different. And that just shows you that even though this is a simple task, it is meaningfully grounded in the full context that we're talking about. Now, what we'll do for our listeners is essentially give them these utterances as inputs and have them function as classifiers, making a guess about which of the 3 colors is the most likely that the speaker was trying to refer to. So in a little more detail, here's the neural listener model. It's again an encoder-decoder architecture. For the encoder side, we can imagine some recurrent neural network or something that is going to consume a sequence of tokens, look them up in an embedding space, and then have some sequence of hidden states. For the decoder, the handoff happens for the final encoder state, presumably. And what we're going to do here is extract some statistics, in this case, a mean and a covariance matrix, and use those for scoring. So in a little more detail, we have those 3 colors as given for the listener. Those are represented down here. We'll embed those in some color space. We could use the Fourier transform just like we did for the speakers at the end of the previous screencast. And then we'll use those extracted statistics from the encoder to create a scoring function. And then we just need to define a softmax classifier on top of those scores. And it will be that module that makes a guess based on this encoder representation about which of the 3 colors the speaker was referring to. So fundamentally, a kind of classification decision in this continuous space of colors and encoder representations. Now, once we start thinking in this mode, I think a lot of other tasks can be thought of as listener-based communication tasks. So even the simplest classifiers are listeners in our sense. They consume language and they make an inference about the world, usually in a very structured space, right? So even like in the simple case of our sentiment analysis, you receive a linguistic input and you make a guess about whether the state is positive, negative, or neutral. That's a common classifier, but thinking of it as a communication task might bring new dimensions to the problem. Semantic parsers are also complex listeners. They consume language, they create a rich latent representation, some kind of logical form, and then they predict into some structured prediction space like a database or something like that. Scene generation is clearly a kind of listener task. In this task, you map from language to structured representations of visual scenes. So it's a very complicated version of our simple color reference problem. Young et al. Explore the idea that we might learn visual denotations for linguistic expressions, mapping from language into some highly structured space, similar to scene description. May et al. 2015 develop a sequence-to-sequence model that's very much like the above, but the idea is that instead of having simple output spaces, we have entire navigational instructions that we want to give. So that's going from a linguistic input into some kind of action sequence. And finally, the serial bar data set is an interesting one to explore in our context. That was a task of learning to execute full instructions. So that's again mapping from pretty complicated utterances into some embedded action that you want to take in a game world. And that could be a very exciting extension of what we've just been covering.